you now understand the STFT and basically how to read spectrograms at a high level. But the first thing I want to tell you about is that we're going to do some processing which makes this representation here look a little bit more like what happens in our ears. And the first thing to note there is that our ears are actually way more sensitive to differences at lower frequencies than at higher frequencies. It's much more difficult for us to distinguish things up here at the higher frequency end than at the lower frequency. And that's really captured in something called the Mel scale. So let me quickly run through this example. The first question is, can you hear the difference between 300 Hertz and 310 Hertz? Okay, so there's a 10 Hertz difference in these two signals. And then we're going to look at whether you can hear the difference between 2000 Hertz and 2010 Hertz. Okay, so let me quickly play you 3000 Hertz signal. Okay, a little bit more comfortable than that siren. And 310 Hertz. Can you hear the difference? Okay. I think it's pretty clear that there's a difference. Now, 2000 Hertz, prepare yourself. Okay, now I'm a little bit, maybe I listened to too much Rise Against or something. I can't hear the difference here. Maybe you can, but even if you can, you will admit that the difference between this signal and this signal here, perceptually, is very different from the difference between these two, right? The difference in perceived frequency is much larger between 300 and 310 Hertz than it is between 2010 and 2000 Hertz. And people realized this quite early on. So what they did was they developed something called the Mel scale that we still use. And the idea behind the Mel scale, which the equation for the Mel scale is really just here. So to go from Hertz to Mel, you take the value in Hertz and you plug it through this function here. You can also go back to Hertz if you've got the sequence in this unit called Mel. So this is what the Mel scale looks like. If you've got a 2000 Hertz signal, then it's like, I don't know, somewhere there, just below 1500 Mel, actually just a little bit above it. If you've got 16,000 Hertz signal, then it's, above 3,500 in Mel. Okay. And what this Mel scale does is, the idea is that if you've got, say, a 10 Mel difference here at this point, then a 10 Mel difference here should have perceptually the same kind of difference. Okay. So the idea is that linear steps on the Mel scale here should correspond to perceptually similar steps. Okay, I have no idea whether that makes sense, so let's just illustrate that a little bit. Here we had 300 Hertz and 310 Hertz, and I quickly converted that to Mel, so it's 401 Mel and 430 Mel. And you clearly hear the difference between these two signals. Okay, perfect. Now here we've got a 2000 Hertz signal, which is 1521 Mel, and a 2010, which is 1525 Mel. So the difference in Mel here is much, much smaller than it is here on this side. Okay, and that makes sense because I can't hear the difference between this. Okay, so the perceptual difference is much smaller. Let me illustrate that a little bit more. Let's just change the frequencies here. Let's make this 1500, and let's make this weird number. Okay, and then let's take 2000, we keep that, and we use this enormous number here. Okay, now let's quickly run through that, and then I'll explain why the fudge I did that. Okay, so what I've done is I've carefully selected these frequencies so that the difference between 1500 Hertz and this 1758 Hertz, this is the Mel and this is the Mel, okay? And the difference in Mel between these two is at, I think, 125. Here I've got a 2000 Hertz signal, and 1646 Mel and 1521 Mel. So the difference between these two is also 125. We've got 4 signals here, but the difference in Mel between these two and the difference in Mel between these two are the same. So let's just listen to them. Okay. So, okay. Now we're going to listen to this signal. Okay. Now what you want to do is in your head, go up this much, but from this signal. Okay. Let's see if that happens. Okay. Let's do this. Okay, so it's maybe not exact, but you can see here that the difference between these two and the difference between these two, in Mel, they're basically equally spaced, and you can hear that it makes a lot more sense. And the important thing here is that the difference between these signals, they're linearly speaking, right, in hertz, the difference here is much larger than the difference here. Okay, and that's all captured on the Mel scale. Okay, now, why am I telling you all of this? So the reason I'm telling you all of this is we're going to take in our spectrogram, our STFT, and we're going to basically butcher it a little bit so that it looks more like what we just perceived. And the way in which we're going to do it is we're going to use something called filter banks. And filter banks, what they look like, they're little banks of filters, okay? They're these triangular filters that are spaced on the Mel scale. So they're also sometimes called Mel scale filter banks, okay? And what they look like is initially they're quite close together. So it's little triangles, okay? And initially they're kind of close together. I'll see if I can draw this out perfectly, but I won't. And then what happens is they start to, as they get to higher frequencies, they start to spread out. Okay, this is quite extreme. Okay, and here on this, on the axis here, we've got it's some amplitude that we're going to weigh things with. Okay, so how this works is the important thing for filter banks are they're these little triangular filters. This is one filter, this is the next filter, and so on. Okay, cool. But the important thing is these little peaks, they are spaced according to the Mel scale. In other words, depending on how you divide things, the difference between this peak and this peak in Mel will be the same as the difference between this peak and this peak in Mel. And this peak and this peak and this peak and this peak and this peak. So they're linearly spaced on the Mel scale, but in terms of the frequency scale, that means that as you get to the higher frequencies, the difference between the peaks needs to get bigger. Okay, and the reason for this is that this is what our ears do, right? We just listen to a bunch of examples. So what we're going to do is we're going to basically weigh our spectrogram or our STFT features according to the filter banks. Okay, so how are we going to do this? What we're going to do is we're going to take the first window, and we're going to do the same for the other windows, but we're going to take this first window, and let's just quickly plot it here. Right, and let's just squiggle it out. Okay. Okay, it doesn't look the same, but you get the point. It doesn't need to be, it can be some other window. Okay, and just as a reminder again, these points are discrete points, right? I drew it as a continuous line, but it's really discrete points. Okay, and what we're going to do is with our first filter, right, which is this first guy here, what we're going to do is we're just going to weigh the spectrum here at the bottom. We're going to weigh it with this filter. What does that mean? So remember that we've got discrete points here, right? So we've got a sample here, a sample there, a sample there. Remember, it's like these discrete samples, right? Okay, and similarly, the filter banks are also actually like little discrete dots, okay? running something like this. Okay, so our first filter will just be there and then zeros. And what we're going to do is we're going to take the first number here, which is 0, multiply that with that number. Take the second number here, multiply it with the second spectral feature. Third, so on. So we're basically weighing the spectrum here according to the filter bank dots. Okay, we end up with a whole bunch of numbers, and then we add them all up. So this first filter basically captures what's happening at these frequencies. Okay. Then for the second filter, do the same thing. So you basically have these little, let's make it orange, these little samples for your filter, and you take each of these dots and you multiply them again. So the first one, again, you start with the first one here, and first orange, second one, second, and so on. And you add them up. Okay. And in the end, what you end up with is, if this was your input, then you end up with as many filters as you have in your filter banks. Okay, so you will specify the number of bins or number of filters that you're going to use. And you're condensing this whole thing into, in this case, you will have 1, 2, 3, 4, 5, 6, 7 numbers. Okay, normally we use 40 or 80, and they're spread from 0 hertz up to maybe 8,000 hertz. Okay, depending on how you sample things. Okay, and that's filter banks. Okay, so the important thing here is that these filter banks are designed so that it can distinguish between lower frequencies a lot better than they can between higher frequencies. So here I've just basically a little bit more beautifully plotted the filter banks, just as a quick reminder here, right? So here we've also got, you can think of it as frequency, and here we've got the basically the DFT's amplitude at different points. Okay, and what you will do is you will weigh them. Here on this plot, I think I've got, let's see, I've got 20 filter banks going from 0 to 8,000 hertz. And here you can see that at lower frequencies, they're much closer together. And then at higher frequencies, they're more spread apart. Okay, cool. So let's run that and let's use stress start. And then what I'm going to do is I'm just going to calculate the Mel Scale Spectrogram. That's what you get out if you take the spectrogram that we had before and you push them through this bank of filters. So let's quickly just see what it looked like before. So before, for the sentence stress start, we had this spectrogram, which has this kind of finer grained content. And then if we go down here, you can see here that now we've bunched them into these little filter banks. Okay, so here we've got time again. Here we can still see this, right? I can still see this. Here I can still see the D and the T and the T. Okay, and here I can still see my vowels, the vowel in E, in dress, and the vowel in start. Now it's important that, let's just look at this axis here. It looks like I just plotted frequency, but you can see actually the difference between these two is 512, but the difference between these two is 1024 and then 2048. So the axis here isn't linear anymore, because what I've done is I've plotted that axis on the Mel scale as well. So this axis is now much closer to the way that our ears would perceive things, right? Differences between 256 and 5112 is a lot more meaningful for our ears than the difference between 4096 and 4096 plus 256. The one other thing that I did here was I took the log. Okay, so this thing is really called the log Mel Scale Spectrogram. Okay, and the reason I took the log, I explained that actually at the start of the video, is because just as our ears treat different frequencies differently, our ears also treat different magnitudes differently. So what we've got here is the log Mel scale filter bank. Sometimes people talk about, in papers, people would just say, I use filter banks, and then this is what they mean. Or they might say I used the log Mel Scale Spectrogram, or I used Mel filter banks or something like that. Then this is really what they mean. Okay, let's quickly just look at what this log Mel spec thing is for this input. Let's just look at the shape. So what you see here is I specified 40 filter banks. And so really what I end up with is a sequence of vectors. Each vector is 40 dimensional, and depending on how long my input is, then this shape here will change. So if I have a longer input, I will have more vectors. If I have a shorter input, then I will have fewer vectors here. Okay. And what you can now do is you can feed in these 40 dimensional vectors into your machine learning model and do some speech processing on that. I'll step through that in a little bit more detail just in a second. Okay, so let's just recap how we got to these 40 dimensional vectors. What happened was we started with the signal and we put it through this process. And really what we end up with is we take the first window, okay, and we put it through a bunch of processing. And what we get out is a vector, a 40 dimensional vector, basically summarizing what happens in that little snippet of audio with a bit of motivation from what our ears typically do. Okay, and then we move this thing along a little bit and again calculated a little window and got a new vector. Okay, and then we did that again for the next window. Right, let's draw that out. It's not perfect, right? But I think you guys will get the point by now. So what you end up with is this sequence of vectors that you can now use as input to your model. So if you're going to do speech recognition, for instance, then you can take this sequence of vectors and feed them into, let's say, a recurrent neural network, which takes these Mel scale feature vectors as input and outputs, based on this sequence, outputs words that's being spoken. If you're doing something like maybe you have two speech signals and you want to say how similar are these two speech signals, do they contain the same word maybe? Then what you can do is, again, you extract this sequence of vectors for the one signal, you extract this sequence of vectors for the other signal, and then you compare the sequences of vectors, and then you can maybe say these two inputs, they contain the same word or not. And just as a reminder, what we have here is this is one of the signals, and we started with some continuous samples, and what we end up with is the sequence of 40 dimensional vectors. We can actually look, write out the first vector here. So we've got log Mel spec, and what we can do is we output our first vector. Okay, and there's our 40 numbers, right? On the slide here, this 9.49, that would be the first number in this first vector right there. Okay, the 7.9 would be the next number, and so on. Okay, 8.75 the next number, and the last number here will be 4.85. The second feature vector, boom, looks like this. So now this last number has changed to 5.2, and so on. And you've got, in this case, 161 of these vectors. If your input was a different size, then you would still end up with 40 dimensional features, because that's how many Mel bands I chose earlier on. But your sequence might be longer or shorter, depending on the length of the input. Let's just quickly recap exactly how we got to this, to these feature vectors. So we started with a little waveform, right, which was our signal. Okay, and then what we did was we pushed that through something called the short time Fourier transform. Okay, so we take the DFT of the little windows in that signal. Okay, cool. Then the short time Fourier transform kicks out complex numbers, but you just take abs, or the absolute value of that, so you get out the magnitude. Okay, and then what you do is we push that stuff through And the filter bank is spaced on the Mel scale. Okay, there are these little triangular filters which are close together when they start out, and then they get progressively further apart according to the Mel scale. I always thought that Mel was a person that came up with this. I don't know, Tracy Mel invented the Mel scale in 1940 or something. But then for this video, I quickly read the Wikipedia article, and apparently Mel just stands for melody, which is super boring, but okay. So in my head, it's still Tracy Mel, but the real answer is that this word Mel just stands for melody. Anyway. So then we've got our filter banks. We put this thing for our filter banks. And if we've got 40 filter banks, then we'll end up with 40 numbers for every one of our windows. If you've got 80 filter banks, then we'll end up with 80 numbers, for example. And then we take the log, okay? And the reason for taking the log is, you guys already know the answer, is that our ears are much more sensitive to differences in amplitude at lower levels than at higher levels. So the log of something looks like this. So at low amplitude values, we're much more sensitive to differences than at high amplitude values. Okay, this is just the log of x, and this is x. Okay, cool. And what pops out of this whole process is a bunch of vectors, okay, which we can now use as input to our speech recognition model or our speech translation model, or whatever you want to do. And these are called the log Mel Scale Spectrogram, or filter bank, or log Mel filter bank features. I'll just call it log Mel Scale Spectrogram.